This is a review for Chapter 5, Integrals. I selected a few sections from the chapter, and we'll go through these sections and try to solve some examples. Okay, here, section 5.3, the definite integral. The definite integral is defined as the limit of the Riemann sums. Here, once for every choice of a partition and every choice of point in each subinterval ck, the Riemann sum is converging to a number j, then we say the j, the limit, j is the integral of f over a to b. The Riemann sum is made in this way. After making partition, for example, in this partition, there's now a case subinterval, and for this one, we are choosing ck, a point in the subinterval, and measure the height, and along with there is now the bottom length is delta xk, and at ck, the height is f of ck. This will make an area here for each subinterval, and of course over there there will be negative area is summed, and if we define the partition, then it may converge to a number. Then the number is the definite integral. Okay. Here in mathematical form, we can write in this way. Here, limit with the Riemann sum. Either we say limit along with partition length approaches 0, or number of subinterval approaches infinity. And so that if the limit exists, then we say that is the definite integral of f over a to b. And we use this notation. Okay. Now, here, when the definite integral exists, then we say that the Riemann sum of f converges to the definite integral. And we say also, in this case, f is integrable over the interval ab. Here. Now, if the given function is continuous over interval, or it is at the most finite many jump discontinuous, then the function f is integrable. Okay. Now, here, let's try to express the limit as a definite integral. Okay, in this formula, here, ck will be changed into x, and delta x will be changed into dx, so that for this one, already the interval is given -7 to 5, so that the quantity must be here now integral over and -7 to 5, and ck will be changed into x, so that there is x squared minus 3x, and delta x will be here dx. Right? So that's the final answer. Quite easy, right? And we'll say again here in Riemann sum, the limit of Riemann sum, the ck will become x in the integral form, and delta x becomes dx. Okay. Now, for this expression, now we'll try to express the limit as a definite integral. Okay. Now, from this one, here we have to find delta x. So that let's say there is delta x for equal subinterval delta x. Then now And here, the interval is now, interval length must be, because that is from 1 to n addition. So each delta x added n times, so that interval length from this one, now n times addition makes interval length is 2, right? Okay, so here you can express it along with many ways, and it's not really unique. For example, now number 1, if we choose interval, for example, here now from 0 to 2, so that is interval length of 2. Then in this interval, if you make n partitions, then the kth one must be here. Now, first one is now 0, but that point must be 1 times delta x. That is now 2 over n. And now that is twice of that, 30 times of that. And in general, in case interval, that point must be k times 2 over n. So that is now ck. Right? We can choose right endpoints. That is a ck. So here, okay, 2k over n is ck. Okay, that portion is ck. Now that portion is ck. So that along with that interval, our choice, the given term is the same as integral from 0 to 2. And then here now, okay, that is now 3 times, that is ck, will be changed into x, and plus now 4 times here, 3 plus, again, that is a ck, so it becomes x, and now the delta x becomes here dx. Okay, that is a choice. But another way we can do it here, secondarily, because 30 is there, probably we may try to get here interval, choose interval from 3 to 5, so that interval length is now 2. In this case, if you make n partitions, then for, in general, kth one, then in the first one, that will be here now 3 plus, okay, and delta x, 1 delta x, so that here 2 over n, and in general, kth one, for kth subinterval, the right end point must be 3 plus k times 2 over n, right? So here, in this case now, this whole thing is basically the ck, so that the given term, the limit of Riemann sum, can be written here from 3 to 5 integration. We chose 3 to 5. And then in the case, the ck must be in this form, so that is a ck. Now ck, so that ck squared, or it becomes x squared. And for the second term, now 4 times x. And here, n over 2 is the same. Delta x becomes now here dx. So that is the integral. Either way, you can express this, the limit, as a definite integral, but the result must be the same. Okay? Okay, that is using some properties of definite integral, we can solve the problem. And there are some the properties, but basically the main idea behind this problem is that if we try to get definite integral from now a to b, then if there is some point c, then here whole definite integral can be made here part by part. Definite integral over there and definite integral over there summed, then this is a definite integral from a to b. Okay, let's try to solve this second one, and that is now for f. We have lower bound from 1 to 9 and upper bound from an interval from 1 to 9, interval from 7 to 9, but there's no 1 to 7 is given. However, that one is now the same as, for that integral, we know here 1 to 9 is given. Now, so that 1 to 9, and then if we try to eliminate from 7 to 9, then the remainder part is 1 to 7, so that eliminate from 7 to 9 and f. Okay. And now here the values are given. For this one is -1. For that one is now 5. So that here -1 minus 5. So the value is -6. Okay. Okay. Right. Okay. Now here, and we may try to get definite integral by interpreting the integral in terms of areas. For example, for this one now, now if we try to visualize the function in the two-dimensional coordinates, then it is given in this way. Now here, x and y axis, and then here from -1 to 3. Now, once x is 0, then there is 1, and then here go down, and here go up like that, so that we have to get the area below this curve. That one is basically the curve like that, so that we can add these two areas. For this point, once x is -1, then -1, so the 2 and 1, so that that height is 3, right? And then now once x is 3, then that height is 7. So here from this side, and that height is 1, so the average height is 2 times length 1, so that left hand side there is 2, right side bottom length is 3, and average height is over there is a 5, so that is 15, right? So that here the that total area is now 17. For this one, is now if we try to make the graph for that one, y equal square root of y equal here square root of 9 minus x squared. Out of that one, if we square, then y squared equal 9 minus x squared over there. Of course, x must be not x. Y must be here larger than equal to 0. And from this one, we can get here x squared plus y squared equal 9, and y is larger than equal to 0. So the pictorially, we can make the thing in this way, is from the half circle upper portion, so we have to find this area. There's a 3, and this is -3. So the given term is the same as whole area is pi r squared. So the pi times 3 squared. Now half of that. So that's the final answer. Okay, here for average value, here sometimes it's called the mean. Now that is integral of f of x and divided by the interval length. That is the definition of average value. Now let's try to find the average value of this function. You can find the average value part by part. Okay, this portion in average value is constantly 1, so that there is 1. Right? Average value must be 1 for that one. For second one, now that one, similarly as in this one, now that is now here area must be now half circle upper portion of radius circle of radius 2, so that is pi r squared. There's 2 squared, and half of that is now the area, the integration, and divided by the length is 4, right? So that here you can simplify this one quite easily. Okay. In fact, that one. Okay, if we finish the computation, that is the first portion is 1, second portion is now pi over 2. Okay. Section 5.4, the fundamental theorem of calculus. The part 1 is here. Once f is continuous on the interval ab, then this integral, if we call it capital F of x, then capital F of x is continuous and differentiable, and its derivative is the same as f of x. That means that capital F is an antiderivative of f, and an antiderivative of f can be written in this form. Now, the second part is given here. F is continuous, and now capital F is any antiderivative of f, then now the definite integral, originally it is defined as the area underneath y equal fx between x-axis, but that definite integral can be measured from this difference. Just right endpoint value of capital F minus left endpoint of capital F. So in this way, we can measure the definite integral. So in here in your level, finding definite integral is related with finding antiderivative. Any antiderivative is found, then you can easily get the definite integral. Okay, here we have a formula here. For example, rather than ax, here we have general h of x and g of x and bottom and top, and after integration, and we try to make a derivative. Then, now here, let's say the capital F is antiderivative of f. Then here from part 2 of fundamental theorem of calculus, we reach at this one. Then now that is same as f of gx minus f of hx. Now we try to make x derivative. Then by chain rule, here capital F prime gx times g prime x. Now f okay. Once you apply here derivative for that one, that can be changed into capital F prime g of x, and here g prime x. Now capital F prime is a small f, so that we reach at this one. Same way we are reaching at that. So here for this form, and we have this formula. let's try to find the derivatives of these functions. That one is quite simple. By using standard technique, you can get it quite easily. Now, for this one, here g of x is x cubed, so that now here the derivative of this term is the same as, okay, instead of t, we are using x cubed, so that e to the minus x to the 6, and its derivative, that's 3 x squared. And then for the other portion, it makes constant so that it'll be 0. So that's the final answer. Okay. For this one, now if we start with y prime derivative, then for that one is constant so that it'll be 0. Now minus, okay, here we replace t with sine x, so that is a sine, okay, sine squared of x divided by square root of 1 plus sine squared x, and then here derivative of sine x, which is cosine x. Right? That's the final answer. Okay, now we have here mean value theorem. Okay, once f is continuous, this is a condition. Once f is not continuous, then this mean value theorem is not true. So f is continuous, then there is point C. Existence of such a point C is guaranteed, and over the interval such that this average value is the same as the function value at C. That is the mean value theorem. Okay. Now, here, definite integral can be applied for the computation of position, velocity, and displacement, and also distance traveled, the total distance traveled. Okay, here, velocity of an object is now here the derivative of the position, here now for an object moving along a line, here s of t is the position. Now its derivative is velocity. So that once you try to integrate the velocity from a to b, then it is position change. So that is now displacement. And once you try to get distance traveled, then now velocity absolute value must be integrated. Time is from a to b, but here now velocity is positive, then it's moving forward, but it's negative, then it's moving backward. Displacement is from here to there. However, the total distance traveled is in the whole thing, so that you have to integrate the absolute value of the velocity. Okay. Okay, let's try to solve this problem. The velocity function is given for a particle moving along a line as here, and t is moving from 2 to 5. The displacement is basically the integration from 2 to 5 of just simply velocity. So that's now t squared minus 40 here plus 3 and dt. If you try to get the integral, then you can find the final answer. Now, for this portion, the distance traveled, and you have to get here now from 2 to 5 absolute value of the velocity. So that there's t squared minus 40 and plus 3 and dt. Okay, so we have to know where this function is positive, where it is negative. Okay. Now, Vt, V of t, that one is now, if you try to get the factoring out, then it's Tt separation, and it's -1, -3. So it becomes here now -4. So that is now t -1 and t -3. So that at 1, at 3, the velocity is 0. Okay. Let's try to make a picture. Now our time is from here 2 to 5. Now it's at 3 is 0, at 1 is 0. So that velocity is given go down, and then here go up like that. It's quadratic. Okay. So from here to there, the velocity is negative. From 3 to 5, velocity is positive. Right? So that one, for this one, this integral, and 2 to 3, we have to integrate negation of that, so that rather than minus of velocity, okay, we change the lower bound and upper bound, so that there is integral from 3 to 2, and the second portion is velocity positive, so we try to get here 3 to 5 integration for that one here, t squared minus 40 and plus 3 and dt, right? Okay, its antiderivative is now 1/3 of t cubed minus 2t squared plus 3t, and then here evaluation is 2 and 5, and now bottom is 3 and 3. That means that here you are evaluating this one at 2 and at 5, is add them. Now you evaluate this one at 3, and twice of the value must be subtracted, right? So you can finish the computation yourself. Okay, now we are reaching at section 5.6, definite integral substitutions and the area between curves. And in section 5.5, we considered the substitution rule. And once you try to substitute some portion g of x by using u, then now here in the substitution, because it will become now the integration with respect to u, so that here you have to find the portion g prime x and dx so that it can be changed into du. Main thing is that here you have to find g prime x dx so that it will be used as du. Okay, now here for definite integral, and now here ab from a to b, for that integral, if we are using now u substitution, then here lower bound, upper bound must be changed correspondingly, and so that, and you have to find the corresponding lower bound and upper bound of u. These lower bound, upper bounds are for x, but after substitution, you have to find bounds for u. Okay. Now let's try to solve this problem. Okay, looks like here, once you make a derivative, then now its derivative is now related with this one quite closely, so that we may start with u is now gx is that portion, so the x cubed plus x squared. Then from this one here, du equal same as 3 x squared plus 2x and dx. So that this portion and that portion is twice of that, so that these two will make 2 du, right? Okay, in this way, you have to find here the derivative of g times dx, so that you can use du, okay? Now, this lower bound, upper bounds are for x, so that once x equals 0, that means that here 0, then u is 0 again. U is defined in this way. Now, x equals 1, then u is 2. So here, the given integral is same as now, the lower bound, upper bound is from 0 and 2 for u, and now this portion is square root of u, and then the remainder part is twice of du, right? Okay, so here the antiderivative must be u to the 3 over 2 and with some coefficient, right? Okay, if we put here coefficients, for example, 4 over 3, then after differentiation, that'll go out and multiplication makes 2. So that this is an antiderivative of this one. Okay, so now we evaluate from 0 to 2. Okay, then that's the final answer. Okay, now for that one here, if we try to use, for example, u equal sine x, then derivative of sine, so that du equal cosine x and dx, so that this portion will be changed into du. Okay, here now, so the given integral, we'll try to use now compute the lower bound and upper bound directly. Once x equals 0, then u must be 0. Sine 0 is 0. Sine pi over 2 is 1, right? And that is now u squared, and this remainder part is du. Okay, so the answer must be 1/3. Okay, that's the final answer. Now, areas between curves. Here, over the interval AB, we assume that f and g are continuous and f is larger than or equal to g of x. Then the area between these two curves can be obtained through the same technique, the limit of the Riemann sums. Here, first we make a partition from A to B, and for each one, now we find some point ck, so that from here to there is height, that is exactly this one, and now the here subinterval length, so that will be area of kth portion, and then it's summed from 1 to n, and then we try to get limit. So in integral form, it becomes now a to b and fx minus gx and dx. Here, you may think this one in this way. From a to b, f minus g will make, for each point x, f minus g will make a straight line here for each x. So these lines are added and summed through this integration. So that makes area, right? Okay, so that's the formula. And here, now in this example, we'll try to find the total area. So total area means that now here some portion f may be smaller than g, then we have to find the area, and so that each portion must be contributed positively. Okay, let's try to visualize the problem first. Okay, that's now from 0 to 3. Okay, let's try to make here. Now coordinates, and now our interval is from here to there, 0 to 3. Okay, 0 to 3. And the parabola is y equal x squared minus 4, so that you're passing that point 2, and here now minus 2. So go down, and here minus 4, and coming up like that. So here we have to get the area, and this one, oh no, not that one. Another curve is now, okay, another curve is x minus 2, so that it's passing right now here minus 2, so that once x2 is 0, so that it's passing the same point right now, so that it is given in this, okay, not that way. Okay, must be passing here. Okay, let's try to make a straight line like that, so that we have to find this area and that area separately and sum them. That's what we have to do. Okay, so that is now, okay, for this portion is larger, but that portion is larger. But anyway, here, okay, if we try to get x squared minus 4 and minus x minus 2, then that is same as x squared minus x, now minus 2, right? So here, from 0 to 2, is the value is negative, so that here, for this portion, rather than 0 to 2, we are using 2 to 0. And here from 2 to 3, okay, so that is x squared minus x minus 2 dx. So that this is total area, and that is 1/3 of x cubed minus 1/2 x squared minus 2x. And we are evaluating 0 and 3, and positively, and 2 and 2, and negatively. Okay, you can simplify, and you can finish the computation yourself. Okay, this is end of the chapter 5. Thank you.